Hello everybody, my name is Héctor Muñoz and I like to tell you about a theoretical investigation of electronic and mechanical properties of zirconium carbide under high pressure. In this work, we have carried out the functional theory of density to determine the effect from 0 to 500 gigapascal. We observed two transition pressures. The monolayer changes from ductile to brittle material as the pressure increases, where the carbon p orbitals are influenced to change the properties of the monolayer by the effect of the pressure. As an introduction, we can mention that zirconium carbide bulk is a very hard refractory material, that their application ranges from medical to engineers fields. The bulk shows a theoretical transition from Roxal P1 to CSCL P2 phase. Although there are several studies on the bulk structure under pressure, there are still no similar studies on the monolayer. We use the crystallographic plane 111 for the formation of B1 phase monolayer. Similarly, the phase P2 was modulated. In the figure 1b, the enthalpy difference is represented. We can see two transition pressure from phase B1 to B2 occurs at 276.81 gigapascals and from B2 to B1 at 400 gigapascals. In figure 1c, the cost of energy is shown. A decrease in energy is observed in PT1. At 0 gigapascals, the greater contribution in the valence band is by carbon p orbitals, followed by zirconium d orbitals. The biggest contribution in the conduction band is by zirconium d orbitals. A valence band gap is observed from minus 3.3 to minus 6.5 electron volts, but it disappears at PT1. After this pressure, the contribution of zirconium d orbitals and carbon p orbitals are very similar, but near of Fermi energy are greater contribution by carbon p orbitals. In addition, elastic constant and moduli increase as pressure increases. In PT1, a change in this parameter is shown, indicating a transition phase, and in PT2 the constant change slightly. For the case of Puch criterion and Vickers harness increase as the pressure increases. At 200 gigapascals they have a noticeable increase, but at PT1 they increase abruptly. After this pressure there is a constant increase. On the other hand, Poisson ratio increase, but at 200 gigapascals it has an abrupt decrease. At PT1 another abrupt change occurs, but it stabilizes after 300 gigapascals. Finally, these are our conclusions. The systems are thermodynamically and energetically stable, but are less stable than bulk material. There are two transition pressures. The first was identified at 276.81 gigapascals, and the second occurs at 400 gigapascals. Thus shows a metallic nature. P2 shows that at 0 gigapascals, carbon p orbitals contributes more states in the valence bands, and zirconium d orbitals in the conduction bands. As the pressure increases, both states' contribution becomes similar. However, the contribution of carbon p orbitals are greater near Fermi energy. The elastic constant and moduli increase as the pressure increases. The zirconium carbide monolayer is a ductile structure, and as its pressure increases, it tends to become brittle. And the monolayer exhibits ionic covalent bonds except for 200 gigapascals, where a metallic bond is identified.